Welcome back, guys. I want to spend a little bit of time today talking about what makes waves special. And again, I'll do some demonstrations in class when we're in person that will illustrate this better, but this is a good starting point. So this is the second part of the wave notes, which you guys should already have. So what makes waves special? Waves can interfere, waves can diffract, and waves can reflect. So interference is going to be when two waves interact. So if we look at our picture here, when they do interact, we call this superposition. This is the adding together of the two. And you can arithmetically add the pulses to find out what they are. So looking at our picture here, we have what I would call a positive pulse and a negative pulse. As they meet each other, they're going to cancel out. And I'll show you guys this in class. And then, as they pass, the positive was going to the right. The positive continues going to the right. The negative continues going to the left, as if they didn't interact at all. This is unusual. So this is not how particles behave. You'd be very surprised if I were to roll a bowling ball at another bowling ball, and as they met each other, they disappeared, and then precisely after that, they reappeared and continued on in the direction they were going. That would be surprising behavior for you. When they're both on the same side, I'm calling them both positive pulses here, when they come together, they're going to become a pulse that is the combination of the two of these, and then afterwards they continue on like nothing happened. Again, this would also be unusual for particles. Imagine rolling a bowling ball towards another bowling ball that was rolling towards it. They come together, become a bowling ball that's twice the size, and then split back into what they are and continue on their way. This is unusual behavior. This is one of the things that only waves do. And here you can see how we'd add these. They ask us to do this a lot in AP. This section's really easy free points. When they add to get bigger, when they're complementary, we call this constructive interference. And when they add to cancel each other out, we call this destructive interference. So in our first case here, our amplitudes meet up. And so if I'm saying that this is 1 unit and this is 1 unit, this one down here would be 2 units. And if this one was -1 units and this one was -1 units, this one would be -2 units. In the same case here, so this would be constructive. In the case here, this one would be destructive. And so if this is 1 unit and this is -1 unit, it would add up to 0. And if this one was -1 and this one was 1, this one would add up to 0. And they can also be a combination of both of them, where they don't line up perfectly. It's actually kind of hard to get waves that do line up perfectly. But again, I'll be able to demonstrate this in class with you guys, especially in the sound unit. So again, here's some more diagrams of constructive interference showing the pulses going towards each other, combining together to be a bigger pulse, and then separating to go on their way. And then destructive interference when they cancel each other out. All right, the second thing that waves can do is they can bend around edges. And this is a surprising thing. And I mentioned this earlier in the last video when I talked about Aquaman. When I said that, oh yeah, that longitudinal waves will be spherical waves. They'll travel in all directions. And I think about Aquaman when he is trying to summon all of the animals in the sea, and he's putting out that message, and it goes out in all directions around him. Well, because waves can do this, when they get to a limit, an opening, a slit often, they'll go through this slit, and when they do, once they get through this barrier, they'll spread back out again. They'll spread back out again. And that's why if I'm facing forward and talking to the class, people over here can hear me, people over there can hear me. And even someone in the hall would be able to hear me, even though the door would be a barrier. And I'll demonstrate this for you guys. We need to know this. For a pulse, if it's a free end, so an end that goes down and can move, and you guys have done the inquiry lab, so I've already had you guys look at this and try this. When this pulse reaches a free end, it's going to rebound and come back the same that it came. So this started as a positive pulse. This is going to come back as a positive pulse. If it's a fixed end, that pulse is going to switch. So when it gets to our fixed end, it started as a positive pulse. It's going to rebound as a negative pulse. And that's going to be important as, I should do red because that shows up a lot better. That's going to be important when we add these waves together and cancel them out in sound. So also, if you have a wave that is reaching the end of its medium, where the medium's still free to move, it's going to be reflected, and the reflection will be the same. If it hits an obstacle, it is going to be inverted. And that's just what we saw with the girl and the wall. If you go from a light section to a heavy section, going from one medium to the other, some of it is going to be reflected, some of it is going to be transmitted. It is going to change the wavelength, but our frequency would be the same. A common way for us to draw waves, especially like I said, like it's hard to draw like particles close together than particles spread out, is to just draw the parts where it's maximums. And so we call this our wave fronts. And so instead of trying to put stuff together and stuff apart, we just drew lines that show us where we have our peaks at. And then later on, when we do light, we'll see that it's often common to draw waves as straight lines as well, which is convenient for ray diagrams. The other thing that waves do that particles do somewhat but don't do as well is reflecting. So when a wave hits something, the angle in is going to be equal to the angle out. The angle in is known as the incident angle, and the angle out is known as the reflected angle. And this helps, so if I was trying to say that people in the hall could hear me talking, diffraction would help spread out the wave, but when it reaches a wall, it's going to bounce off. When it reaches the lockers, it's going to bounce off. And that's also the reason why a lot of the demonstrations with destructive sound are hard for me to do in here, because there's walls everywhere, and I just want the waves to interact, but there's going to be ones that are bouncing off the back of the room that are coming forward, which are also going to be problems for us.